All right, our final talk for the session is from Konstantin Getman from Penn State, who is going to tell us about the temporal evolution of X-rays on young stars.
Hi, Kevin. Did you see my slide?
Yeah, they look good.
Okay, cool. Thank you. So temporal evolution of X-ray activity in young stars. I'll be talking about young stars, and I'll be mentioning both flares and quiescent emission. So my collaborators are listed here, and the content of this talk and the related type poster is based on our 3 recent papers, also listed here. So young stars, called premium sequence stars, they're still contracting, they're powered by gravity, they're fully or partially convective, they're fast rotating, and they're very powerful X-ray emitters. And we detect X-rays with Chandra X-ray telescope, and this is called soft X-ray band. And soft X-rays are emitted by optically thin thermal plasma that is confined within coronal magnetic loops like on the sun. So if we look at a typical X-ray light curve of a premium sequence star, we can see this lower level of X-ray emission indicated in green, which we call characteristic, as a superposition of numerous unresolved weak flares. And on top of it, from time to time, we observe superposition of larger flares, which we call large flares, X-ray flares. And my primary science topic, temporal evolution of X-ray activity, is actually based on time averaged X-ray luminosity between large flares and characteristic levels. But I will dedicate a separate slide specifically related to large flares. So motivation for the temporal evolution of X-ray activity in young stars is as follows. First, we have to acknowledge that premium sequence stars, they undergo rapid interior changes. And those changes, they will affect internal dynamos, which generate magnetic fields. Internal dynamos, in turn, they generate magnetic fields, which affect surface X-ray activity. So by studying X-ray surface activity, we can say something useful about dynamos. For instance, when a turbulent dynamo on fully convective premium sequence stars transitions to solar type, alpha omega type dynamo. We can also make new insights into the information about X-ray coronal extents on young stars. Our previous results suggested that X-ray coronal extents on young stars is quite different from those of contemporary sun. We can also provide new input calculations to the X-ray effects on disks and planetary atmospheres. And I have to mention that previous studies of such sort, mass stratified X-ray emission in young stars, were made. They're shown here, listed here, but they used very poor cluster samples, typically a few clusters per study. So in our study, we use rich samples of clusters. They could be divided into 2 portions. One portion is very young, less than 5 million years old clusters. They reside in so-called mystic sphinx star-forming regions that we've targeted with Chandra large projects for many years. And we've written lots of papers, but typically they were dedicated to star formation, cluster star formation topics. And then the second portion are older clusters that we recently taken Chandra data of. These are 10 open clusters with ages between 7 and 25 years old. And this is just an example here, an image of a Chandra image ACIS-I detector that shows a cluster. And typically we see hundreds and thousands of X-ray point sources, and we apply our custom tools to extract X-ray photometry and estimate X-ray luminosities. And then we combine Chandra data with multi-wavelengths data. Like for these younger, more absorbed mystic sphinx clusters, we use near-infrared and mid-infrared data. For less absorbed older open clusters, we use Gaia data. And that allows us to perform membership analysis. So to count, identify members in these clusters and also identify X-ray non-detections. Not all of them are X-ray detected. We also estimate bolometric luminosities, stellar masses using so-called color magnitude diagrams like this. And we always construct so-called mass distributions and to ensure that they're consistent with nearly universal initial mass function. So, and this is one of the primary results here shown at the central image as inferred X-ray luminosity as a function of H. It's given for 4 different mass strata here, and gray circles indicate LA, mystic sphinx clusters, and colored circles indicate open clusters. And so first result is very obvious. You can see that for the first few million years, X-ray luminosity stays constant with time. But stars contract. And the most reasonable explanation for this is that X-ray luminosity is not responding to the contraction of stars because X-ray emitting structures are very large. This is actually consistent with the theoretical MHD simulations of fully convective fast rotating stars, where it suggested that such stars would create strong polar spots, and those spots will support gigantic dipolar loop structures that will emit X-rays. And it's also in line with our own studies of large flares from young stars, from very young stars. And our flare modeling showed that X-ray coronal emitting structures can extend reach the altitudes of several to 10 stellar radii, and at the same time efficiently withstand centrifugal forces thanks to the strong magnetic fields. Then we go to later stages of evolution for these less massive stars, and you can see that X-rays drop moderately with power slope about minus 0.6. We find that this is actually consistent with the temporal change of stellar volume. So since these stars are fully convective, we presume the turbulent dynamo is still running inside, but this dynamo is dying at a rate of volume, and everything becomes weaker. Stellar spots become smaller, magnetic fields become weaker, and X-ray coronal extents become smaller. And then finally, for late stages of more massive stars shown here, the X-ray drops even steeper with the slope of minus 1.8. And this slope is actually consistent with the drop of X-ray emission from older stars, main sequence stars, like for instance in study of Gödel, where you can see X-ray luminosity is a function of rotation rate and emission drops. For older stars, rotation rate is a surrogate for age. And the slopes are similar, so we find here that for this mass age, for this age range, many stars actually already developed radiative cores. They're only partially convective. And so at this stage, it's more likely that turbulent dynamo transforms to solar type alpha omega dynamo. So now I switch and I mention large flares that previous two presenters talked about so much. So we've studied so far large flares from very young stars with ages less than 5 million years. We've identified from our large samples of thousands X-ray detected stars in these mystic sphinx star forming regions. We identified over 1,000 large flares. We call them super flares. This is a frequency of flare versus energy diagram. And Max mentioned that for optical flares on older stars. Here in the bottom left corner, we see the frequency of flares in solar type stars, like on our sun. Those brown curves were obtained through Kepler survey of numerous old G-type stars. Whereas our results for young primi-sequence stars are shown in the upper right corner. They are mass stratified. And as Max mentioned, you also can see that young stars, they're actually the most powerful X-ray emitters, and they produce the most violent, most powerful flares. Like for instance, here you can see immediately that the frequency of super flares with energies 10 to the 34 is at least 1 million times larger on young stars than on that of the old sun. And then old suns, they don't produce very powerful X-ray flares like with energies 10 to the 35 or 10 to the 36 because they just don't have enough power, enough strength. Primi-sequence stars, young stars, on the other hand, they produce these mega flares. We call them mega flares. and they produce like 3 megaflare per year. And we find that the contribution of megaflares to the entire X-ray energetics is about 10-20%. So this slide is with regards to calculations on, related to planetary atmospheres. First, I want to mention a couple of papers, Tu et al. 2015 and Johansson et al. 2021. They use modern theoretical rotation evolution models, and they parameterize those models and adjust parameters based on X-ray calibrators, on X-ray empirical data. But they did it they used only 3 empirical clusters in our age range, Taurus and Lagoon 2 million years old clusters, and HPR 13-year-old cluster. And so, and they also produce X-ray luminosity as a function of age. Their model depicted here as red curves for different mass strata. And our purely empirical data for numerous clusters are shown as black and green dots. And you can see there is some deviation present, like for instance, for this mass stratum, X-ray luminosities, median X-ray luminosities for our empirical clusters is systematically lower than what model predicts. Our spreads are typically larger than that's what model predicts, and the model overestimates significantly X-ray luminosities for very young stars. So we encourage the authors of this current rotation evolution models to use our data as empirical calibrators. Then a couple of items related to planetary atmospheres. Like for instance, if we look at this planet HD 63433c, around relatively old compared to our primitive sequence star, solar mass star. Recently, through Lyman alpha absorption measurements, the authors of this study found a huge mass loss rate of hydrogen, primordial hydrogen atmosphere from this planet. If we scale X-ray luminosities of this host star to X-ray luminosities of our young primitive sequence stars, we find that these young primitive sequence stars with mass of 1 solar mass star, they can evaporate planetary atmosphere of an Earth-like planet within 2 million years. And megaflares, as I mentioned, they contribute at least 10-20% to primitive sequence X-ray energetics. But megaflares are very highly nonlinear events. And just the duration is few days. And if the response of the system of the atmosphere is rapid to such events, that their contribution to the whole process could be much more substantial. And we encourage authors of such calculations to incorporate those nonlinear events in their calculations. So this is my conclusion. We use numerous young stellar clusters, Chandra data for these clusters, and we find that X-ray luminosity decays with age in a different way, depends on the age range and depends on mass range. Like for instance, it could be due to extended X-ray coronas or due to dying turbulent dynamo or due to transition of turbulent dynamo to alpha solar type dynamo. We find that megaflares contribute at least 10-20% to the X-ray energetics of young stars, but they may affect planetary atmospheres strongly if the effect of the planetary atmospheres to those flares is rapid. Also consider that those flares, they produce much more hard X-rays, and those X-rays, they penetrate atmospheres better. We encourage authors of rotation evolution models to use our empirical data for model refinements. And young Earth-like planets, they can lose their primordial hydrogen atmospheres within the first few million years when they orbit young solar mass primitive sequence stars. That's it. Thank you.
Thank you, Konstantin. All right. Ilsa, yeah, you can go ahead and just ask your question.
All right, I'll keep it quick. Konstantin, thank you for the talk. I'm actually very interested in the sort of intermediate age range, that 10 to 20 mega year window, where I'm surprised at how X-ray luminous they still are. Are there any mega flares that occur in this window? The reason I'm interested is that this is post-gas dissipation. And so I'm wondering, are these mega flares rare enough that you might have some systems that may undergo that, mega flaring event, and perhaps, strip volatiles from small terrestrial planets, versus like some systems that are lucky and, they're rare enough that they never occurred before the star switches to a solar dynamo or something. I don't know if that was well phrased, but I'm just I'm curious and connecting this back to the astrobio side.
Right. Hi, Elsie. So you're asking question about an age of 10, 20 million years, that sort of age?
Yeah, post-gas dissipation. Because, before that, your exoplanets are nicely embedded in the gas disk and they're shielded.
Right. That's true. So we'll see about that. The problem is that so far we've analyzed flares from very young mystic Sphinx stars with ages less than 5 million years. It's our future work. One of our future works would be dedicated to analyzing large flares from these open clusters with which I've mentioned previously. So it's a future work, so I cannot tell how much of mega flares, what's the frequency of super and mega flares and these older 10, 20-year-old stars yet. So I cannot answer this question yet, but that's in our list to do.
Thank you. Cool. I think it'd be very cool to look at.
Of course, it's obviously will go down. The frequency will go down, but the rate of it, I don't know yet. Wait in a couple of years, I will give you an answer.
Okay. Don't see any other specific questions.
I wanted to mention Mark's previous work on optical flares from old stars, and there was some extrapolation from energies 10 to the 36. By the way, those were bolometric energies in optical band mainly, and if we transform them to X-ray energies, you have to apply a factor of, say, 10, 20. For those older stars, bolometric energies of 10 to the 35 would imply X-ray energies, say, 10 to the 34, 10 to the 33. You can see, but young stars, they have X-ray energies of 10 to the 35, 10 to the 36. So I was curious about, can young stars actually produce mega flares with energies 10 to the 39, 10 to the 40? And the question is unclear to me. We actually didn't find any empirically. So there could be some exhaustion, but even if magnetic energy is present in magnetosphere, there could be not enough magnetic energy that would be released during magnetic reconnection. So such mega flares might not ever be produced. So same story goes for older stars when there was Max made extrapolation towards higher energies. Those might really do not exist. That's it. Thank you.
Yeah, I really agree with. I replied in the chat. That's something I talked a lot with theorists about as well, whether there's enough magnetic energy. And I think that from theory side, there are predictions that it would trail off at some point. And we've also not seen this yet in tests, but we haven't had like the long enough baseline yet. But with the extended missions where we come back years and years after, that's something we hope to probe, whether we can see this drop off. Just like we see the drop off, for the smaller energy flares, there is observational bias, but with injection recovery tests, we can model that out. And then we see actually this is a broken power law for the smallest energies. We wonder if we will see the cutoff for the biggest energies.
Right.
But so far, the test baseline wasn't far enough. But it could well be that we never really reached this zone.
Right.
Okay. So we have the room for